Hello everyone, welcome back to Piece of Physics. In the last video, we just covered the accelerated motion. Okay, in that particular video, we just see like how to define accelerated motion. There were two type of accelerated motion. One was uniformly accelerated motion, and second one was the non-uniformly accelerated motion. Okay, so basically, in the uniformly accelerated motion, the change in the velocity is equal in equal interval of time, right? So such kind of motion is basically known as uniformly accelerated motion. Okay, and in the school level, okay, we have three kind of, and in the school level of physics, we have learned about three kind of equation of motion which are basically applicable to the uniformly accelerated motion. Our first equation is v equals to v naught plus at. Our second equation is x equals to x naught plus v naught t plus half a square. Our third equation is v square plus v naught square equals to 2a x minus x naught, right? And here the v naught is the initial velocity. Okay, v is the final velocity, a is the constant acceleration, x is the final position, x naught is the initial position, t is time interval. Okay, so these are the three equations we basically applied to the uniformly accelerated motion, and that's how we deal with the problems. Okay, now we are going to derive these equations using two methods. First is second is graphical method. In this video, we are going to derive these equations using the calculus method. Right now, let us dive into this. Now, right. So basically, so basically, the instantaneous acceleration is a equals to dv by dt. Okay, dv equals to a dt. Right now, I'll integrate this particular equation like this from v naught to v, and basically time interval is from 0 to t. I'll put it, acceleration a outside the integration. Basically, it is the constant one, right? So if I'll integrate this equation, then I'll have v, lower limit is v naught, upper limit is v, and here I'll get a into this is t from 0 to, okay. So I'll put first v minus v naught. This is a into t, okay, and I'll get v equals to v naught plus a, right? So our first equation of motion is this one. Now let us derive our second equation, which is x equals to x naught plus v naught t plus half at square. Okay, we have the equation v equals to v naught plus at. Okay, and this is dx by dt v naught plus at. Okay, now we will can write this equation as dx equals to v naught dt plus at dt. Okay, So I'll integrate this particular equation like this here. Okay, this is from x naught to x, like displacement varies from initial position x naught to x, right? Our time interval was from 0 to t, and here I'll put again 0 say. Okay, so if I integrate dx, then it will be only x, and we will have lower limit as x naught and upper limit as x. This is v naught into t, and the limits are from 0 to t, plus this is a into this is t square by 2, limits are 0 to t, right? So here I'll put this is x minus x naught, okay, and this is v naught to t plus half it is square. Okay, so the equation will be ultimately x equals to x naught t plus half it square, right? So this is the our second equation which we can derive the using the earlier equation. Okay, so I can write it as equation number 2. Now let us derive our third equation. Our third equation is v square minus v naught square to 2a x minus x naught. Okay, so we have acceleration equals to d by dt, and this is dx by dx. Okay, so this equation is like basically dv by dx into dx by dt, and the acceleration will be, okay, so the dx by dt is v into this is dv by dx. Now I can write this equation as v dv equals to a dx. Okay, this is from v naught to v, because velocity, initial velocity is v naught and upper velocity is v. Okay, upper limit is our final velocity which is v, and our displacement varies from x naught to x. Okay, this is v square by 2, limits are from v naught to v, this is a into x minus x naught. Okay, and the if you put limits here, then it is v square minus v naught square to a x minus x naught. Okay, this is v square minus v naught square equals to 2a x minus x naught. So finally this is our equation number 3. Okay, so these are the three equations which we can derive using the calculus method. Also remember, these equations or this calculus method, like this one or and this one, you can apply to non-uniformly accelerated motion as well, right? So the calculus method has that kind of benefit which you can apply to the uniform accelerated motion as well as non-uniform accelerated motion. So that's all for this particular video. Okay, in the next video we will derive these equations using the graphical method. Stay connected to the channel. Thank you so much.